Just do my. There we are.
I see your slides. Yes, they look good.
Jolly good. Okay, well, good afternoon, everybody. It's a bit daunting to follow such an impressive speaker, but I'll do my best. This morning we heard some very good talks about detecting pulsars with very large dishes. So why is this talk about small aperture pulsar detection? Because it's possible, you might say, but no, the real reason is that I've got a small back garden and I can't get a dish in it. So that prompted me to see just what was the minimum sort of system I could produce that would detect a pulsar. So in this talk, I'm going to tell you how I collaborated with others. I didn't do it all myself, to check what minimum aperture was required, how to design a working system, the mistakes I made, so hopefully you won't make them, and the achievements of my betters, some results, but most importantly, how to be sure you've caught the fish. To add confidence with this, I've discovered a new half-fold correlation algorithm that points a finger at a good pulsar acquisition. I got interested in pulsar detection about 5 years ago in the SARA forum. Am I talking too loud, Rich?
Perfect.
Okay, yeah. So prompted by an unresolved discussion in the SARA forum about pulsar, the feasibility of amateurs detecting pulsars. About that time, I'd finished some hydrogen work, and whilst I was doing it, I was collaborating with a young engineer in Argentina who happened to be looking after the two 30-meter dishes in the Argentine Radio Astronomy Institute. His name was Guillermo Gancio, and he'd also done some work on detecting hydrogen, and we were both using the RTL SDR, which we heard about this morning. So I shot him an email and I said, could you point your dish at Vela and collect me some data? And then from that, I maybe work out what was the minimum receiver you needed to be able to detect a pulsar. And this he did, and with the result was, after a lot of work tuning software, let me see, was this, popped out of the noise base. The thing about this is if you get the period wrong, you don't see anything. It's got to be nearly right before you see anything, but it's got to be exactly right to get something like this. So from this, we chatted together and we worked out that based on the performance of his 30-meter antenna and the receiver that he had, and using the same SDR, that we needed probably at least a 3-meter dish, 3 or 4 dongles bandwidth, and several hours of tracking integration to be able to get a pulse about 1/10 of this size. So we followed on from that. I think I missed the slide, yeah. So what I'm going to talk about today is, first of all, I'm going to run through the radiometer equation, the pulsar radiometer equation, just to see what's theoretically possible, and then look at the key system drivers, what we need to, how we need to design a system to be able to detect the pulsar, look at what receiver components are available. Software is a bit of a problem here because there's a lot of specialized software, but there is a lot of software available, and I'll talk about that. And then I'll go on to present some results and how to validate that you have got a pulsar detection. Next slide, I was going to tell you a bit about pulsar the Pulsar Basics, but that's been well covered this morning. But what I will say that Jocelyn Bell, as she was then, she discovered the pulsars, it was 53 years ago. But her antenna was 2,000 dipoles, as we heard this morning, and 16,000 square meters. And if you want to know what it looks like today, look behind me. That's her array, or what's left of her array. I actually visited the place a couple of years ago and managed to take this picture, and I thought it would be very appropriate for today's conference. Okay, so when you're looking at the detail of pulsars, you need to know what their specific characteristics are. We heard this morning they're very high stability and it's a fairly irregular pulse train. The rotation rate and the period is Doppler shifted by the Earth motion, so on a day-by-day basis you have to make some period adjustments. It's basically broadband noise and a bit more powerful at the low frequencies than it is at the higher frequencies. It scintillates, you know, passes through the universe, and the amplitude hits electrons and things like this, whatever's in space, gradually, and so in fact it varies in amplitude with both frequency and time. It's dispersed, we heard that this morning. The lower frequencies are delayed on the higher frequencies, and it's very, very weak compared to other radio astronomy sources. So this is the Lorimer-Kramer radiometer equation. The way I presented it here is SNR is signal to noise ratio. The signal to noise ratio, and I'll just pick out the main components. There's the pulsar mean flux, the antenna aperture, the integration time, the RF bandwidth, and the receiver system noise temperature. They're the key parameters. The factor on under the square root sign accounts for the fact that the SP is mean power and it's a pulse, and so to a certain extent this is a measure of the peak pulse power. But it also implies that in the analysis that you do, that the final processing bandwidth is restricted to just past the pulse. So a 1 millisecond pulse, you need a 1 kilocircle minimum bandwidth. It's implied in this. But this equation is making the assumption that you are tracking the source. When you have a small aperture, you have a wide beam width, and it's best to work in the drift scan mode, where you point your antenna at the culmination point of the pulsar and let the Earth scan you across. If you do that, then this equation is modified, and this is a drift scan version. It's exactly the same equation, but I'm just taking into account now that the antenna aperture is the beam width is now frequency dependent, and because it's the Earth's rotation, then the integration time doesn't come into it. It does come into it. You need to record for the total time that the pulsar is within the antenna 3 dB beam width, and this factor 736 takes that into account. So it's modified slightly. There are two other factors as well as the system noise temperature, the bandwidth. The frequency, I said, is more because for a given aperture, the beam width is frequency dependent. So that's why that factor comes in. There's a factor B, which is a factor less than 1, and it accounts for the fact that the beam width roll off at the edges is 3 dB down, and so you don't get the full power for the scan time. And this other factor R is if the antenna you're using has an elliptical beam shape. I'll show you later that you could have a wide azimuth beam shape and a narrow elevation beam shape, and if you do, then that factor R is the ratio between the two. Now I've used this equation to put in for Vela, the strongest pulsar in the southern hemisphere, and BO329, the strongest pulsar in the northern hemisphere. And here I've got signal to noise ratio against the effective area in square meters. We're assuming a very good system with a system noise temperature of 100 degrees Kelvin and a 2.4 megahertz RF bandwidth. So this is the curve that we expect. So you can see that with a 1.5 meter squared aperture, you ought to be able to get about a 10:1 signal to noise ratio for BO329 and a 20:1 signal to noise ratio for the Vela pulsar. These two lines at the bottom, the lowest one is at a signal to noise ratio of 3, and that's roughly the peak of the noise, the folded noise at the end of the day. And the next line is at a signal to noise ratio of 5, which you can be reasonably confident if you see a signal with a signal to noise ratio of 5 that it's possibly a pulsar. But we'll go into that a lot later. So if you live in the southern hemisphere, you're about a factor of 2 better off than in the southern hemisphere. So that's theory. What about results? I should have said that was all at 400 megahertz, an RF of 400 megahertz. What's been achieved? Now, this blue line is assuming that you have a receiver tuned to 422 megs, a 2.4 RF bandwidth, and 100 degrees Kelvin system noise temperature. Now this in fact predicts the performance of an Italian radio astronomer, Andrea Dell'Immagine, who's probably the first pioneer of small aperture pulsar detection. And I'll go into it in a bit more detail later, but that's theory, and that was his result. Recently, he's used another antenna with an AirSpy SDR, and with the increased RF bandwidth, then the theoretical curve is raised, and he's achieved, and this spot shows his achievement with an antenna of 0.8 square meter squared. So you can see the theory and the practice, if you do it properly, lines up. If you don't do it quite properly, the bottom curve, the lowest one, is the result that I've achieved. I have a 600 meg RF, a 6 megahertz bandwidth, and my system noise temperature is a very high 175 degrees K. I still haven't managed I have managed on a couple of occasions to hit the line, but my average measurement is between 4 and 5 signal to noise ratio. So those are actual results against the theory. The bottom curve here probably explains why, with the Guillermo Gancio's data with his 30-meter dish, that we came to the conclusion that we really needed a dish with about 5 or 6 square meters aperture, 3 meter aperture, and this curve assumes a drift scan mode, which the beam width is far too narrow at this frequency. But if you do tracking, then the curve rises above this, and you would get about a 4 or 5 to 1 signal to noise ratio. Okay, so that's theory and practice. What
Peter,
about...
One second, I got a question from Wolfgang. It sounds appropriate for now. It says, Peter, as you explained, your integration time is determined by the transit time of the source to your beam width. Have you accounted for the declination, which will have an impact on the transit time?
Yes, yeah, I'll come to that later on. Yeah.
Okay.
Yeah. So one of the important choice is the antenna, is the aperture, as far as I'm concerned, and that was the reason for the title. On the left, I show a horn. It's made of lightweight polystyrene material covered in aluminium foil. This is Rishi Patel's horn for 1420 megs. At 400 megs, the aperture would still be the same. We're looking for that sort of aperture. But to make a better match to space, it probably needs to be about 2.5 meters long. So it could be quite large and bulky. But a horn has got quite a reasonable antenna efficiency. The dish is, the parabolic dish is good with very large diameters, but at small diameters where the diameter is comparable to the wavelength, the feed blockage is far too much, and the efficiency and the total performance is very poor. An offset dish ameliorates this to a certain extent, but it's still probably not a good choice until you get up to about 3 or 4 wavelengths. Oops, go back. The Yagi has got a lot going for it. It's lightweight, easy to make. The electrical aperture is much larger than the physical aperture, but it's got some bad points, and that's side lobes. This is a plot of a professional antenna at 600 megahertz, and this is the E-plane beam width, and the beam width is roughly 28 degrees. The gain is around about 17 dB. Now, to understand what the effect of side lobes are, if we make the assumption that these side lobes are at a level of minus 20 dB, the antenna beam width is 28 degrees. We know there are 41,000 square degrees in a sphere, so we can work out what energy is in the side lobes compared to the main beam by quite a simple sum, and it comes out that the efficiency of this antenna, assuming minus 20 dB side lobes, is about 66%. And what this means is that 34% of the energy is going in the side lobes. In deploying an antenna, we pointed up to the sky at very high elevations. So most of these back lobes point towards the ground. And if we assume that, say, half of them point towards the ground, you can work out the ground is at 290 degrees, then half of them are pointed towards the ground, then the side lobe temperature can be as much as 50 degrees. If, like me, you have a small garden with a high horizon, my horizon is about 30 degrees, I've got the house quite close by, then this term could really get high. And this is the reason why my system noise temperature is so high. Unfortunately, the Yagi had a lot going for it, but it's not good for this application. There are other antennas that are much better that have got low side lobes, and other people have used these. This is the 3D corner reflector antenna, and that has an effective area of 5 lambda squared. It's frequency limited. So if you try to use it at high frequencies, then you just run out of effective aperture, because the sides are limited to a 3 lambda length, and that limits the physical aperture. So at 400 megs, the effective aperture is about 2.5 meters squared. At 600 megs, it drops right down to about 1.2 square meters. The other antenna that has been used, that Andrea Dell'Immagine has used recently, is the double biquad. This again has got good side lobes. This is a metal plane, and in operation you can put wings round the side to lower the side lobes even more. But similarly, that is aperture limited, and at 400 megs he achieved an effective gain of about 13 dB and a effective aperture of about 0.8 of a square meter. Oops. The other possible antenna, I don't know of anyone who's used this, but it was suggested to me when I did one of these presentations before, and that is the backfire antenna. The backfire antenna exhibits good side lobe performance. It's effectively a Yagi pointed at a reflector, and it's a resonant structure, and it's purported to have very high gain. So with high gain and low side lobes, it could be quite a compact solution. So what does a total system look like, a small aperture system? We can start off with our 3D corner reflector antenna. This is Andrea's 3-corner antenna. You'll see it's laid back by 45 degrees because in fact it produces a beam at 45 degrees relative to the bottom plane. So laying it back by 45 degrees effectively points it to the zenith. I've used a mini circuits low noise amplifier. This has 0.4 of a dB noise figure, and it can go right at the end of the antenna feed. This should be followed by a good filter. This is a 5-element interdigital filter that I made from design data that is easy to find on the internet, and it worked beautifully. It has 6 megahertz bandwidth and over 50 dB rejection, with about 2 megs from either side. This can then feed into what I've shown here is 2 eBay amplifiers, about $15 to $20, purported to be 0.6 of a dB, but after low noise amplifier, these are more than adequate, and they feed into an RTL dongle into a computer. Now in operation, these are all connected together, of course. The data recorded, the data produced by the RTL is recorded on the PC, and this then goes into processing to recover the pulse. What I've shown here is a software package written by Michael Clausen, who lives in the Netherlands, and basically it takes RTL binary files and produces and does the dedispersion, folding and data presentation. So that's basically all the system is. It's very, very simple. In my case, I wanted a wider bandwidth, so I've stacked a few RTLs together. I've stacked 4 here, but in fact, I only used 3. The RTL on its own has got some limitations. it drifts in gain and it drifts in frequency. The other thing is that it dissipates more power when it's recording than when it's quiescent. So the way to use it is to rip out the crystals, put in either a temperature compensated crystal to drive them, and that can give you half a part per million stability, or you can use a GPS disciplined oscillator. I've actually got a switch here that switches in either. And if you put heat sinks on all the major components in here, and you put lots of fans and pass lots of ambient air through it, then you can do a recording over 2 or 3 hours and the results are quite stable. Alternatively, you can use the AirSpire, and there are lots of other SDRs on the market these days, as we saw this morning in one of the talks. So we've got the system all built up. How do we test it? There's some free software, the SDR Sharp software. It accepts the RTL SDR, and it accepts other SDRs as well. And you can tune it for whatever bandwidth you require. And you can use this with your system to determine what the interference is like in the band that you choose. And in fact, it can also be used to check the sensitivity of your receiver system. There's the Y-factor method of assessing the antenna and the system noise temperature, and it's quite capable of doing that function as well. I saw you got Radio Eyes as a prize today. It's an excellent tool, and this is where I explain Wolfgang's question. You can in fact put the polar pattern of your antenna on this, and you can, by modifying this, you can determine the time that it enters your 3 dB beam width and the time that the pulsar leaves your 3 dB beam width. And you can check this against the calculated time for the expected 3 dB beam width. And you can point it in elevation so that you get the maximum exposure. The other thing it can do, it has with the tools, you can program in and ask it to find the BO329, and it'll tell you what time it culminates and how long you've got to wait for it. And so you can do all your planning with this bit of software. If you don't get it free, it only costs a nominal amount, and it's well worth the value. So we've got our SDR. What does the data look like, and what does the processing got to do? Well, the first thing you have to do is to detect the video. The SDR samples the in-phase and quadrature components at the RF, and so you have to square and sum these to effectively do the square law detection process, and then you pass it through a low-pass filter before you process it further. And what I've got here is some of the data that I've collected. And what it shows is that the DC level of this component, because I've done a straightforward detection, the DC level is proportional to the system temperature plus the sky temperature, and it includes the pulsar temperature. The amplitude is now determined by the bandwidth of the low-pass filter. And in this case, the RF bandwidth was 2.4 megahertz. The integration time is a millisecond, And so there's about a 50 to 1 reduction in amplitude. Now, if you've got a 30-meter dish, you will actually see the bursts of pulsar noise on this plot. But with a 1 meter square aperture, you've no chance at all. It's the pulsar effective temperature is about 0.05 degrees. The peak amplitude is about 0.05 of a degree Kelvin per square meter per polarization. So for the 1 meter squared, it's 0.05 degrees K. This is 2 degrees RMS. So the peak to peak noise is 6 times that. So that's 12 degrees RMS. And we're looking for a pulsar at 0.05 degrees Kelvin. And the way we recover the pulsar is the folding algorithm. Now, the folding algorithm can't be beaten. I've looked at lots and lots of processing methods to see if I can get a better signal to noise improvement than the folding algorithm, and you can't. Basically, what the folding algorithm does is it takes your data record over a time t, it cuts it up into exact periods of the pulsar, so that if you imagine, you can't see the pulsar, if you imagine the pulsar, it will always be in the same place in all of these blocks. And because this is now a digital signal, we can do with it anything we please. And so we'll cut them up and stack them all on top of one another. And the pulsar amplitude increases linearly. The background noise only increases as the square root. So the signal to noise ratio improves as the square root of the number of folds. And, you know, we're looking at, say, 10,000 periods, and the square root of 10,000 is 100. So it'll be your noise from the previous pulse will go back down by a factor of effectively go down by a factor of 100. So what other software is available? Well, I've spoken for testing. We've got the SDR Sharp, and and for running on Windows, you'll need to download the Zadig driver. But all of this is available on the internet. For data recording, the Osmocom have produced a set of RTL tools. This is one of them. This is the one that collects the data, and that can be collected from Osmocom. For processing, I've written de-dispersion and folding algorithms. But recently, Michael Claassen has developed these 3PT analysis tools that produces this lovely response. And I recommend anybody who wants to go into this field to download that from Michael's webpage. There's other software available. We heard this morning that GNU Radio there's some software written for that. For display, you can use Excel, MathCAD once you've got these downsampled C files. You can do your own programming, C and Python, and we're going to hear about AstroPy later on, tomorrow, I think. But the professionals have had a lovely suite of tools that are available. You can download them and use them. You heard about Presto this morning. Tempo is a software program where you can determine the pulsar period for any acquisition process you want to go for. So here's what I spoke about Andrea's system. This is his antenna again. He lives on a mountain in Italy, and I visited him, and it's a super site he's got there, but he still suffers from RFI. But his automatic observatory had run in for 2 years, from about 2016 to 2018, and you could log into his web page and see the daily results. And with his system, he was probably the pioneer of small aperture pulsar detection. But with his system, as I said, he gets really good signal to noise ratios. It's quite easy to show that that is really a pulsar. His web page is very good as well, because this is the sort of presentation, the daily presentation he produced. I ought to mention his son Giorgio, who actually designed and wrote the software for this page. And he's a young teenager and he's impressive. But what it does show is the scintillation that I spoke about. So this is the recording time. There's not a lot of signal at the beginning and at the end, but this shows the scintillation. There are some periods where the pulsar is very weak, but the folding program integrates all of these. So to validate, the key thing with small aperture is validating. Is it a pulsar, or is it noise, or is it an RFI spike? With a strong signal, you can use the professional software and use the Presto pretfold plot, which I'm glad it was explained this morning. Here you can see the pulse. It's a nice, really big, strong pulse. This is the time waterfall. And it's interesting, you can see in here that there were periods of interference. This is the frequency one, and you can see there are, again, some background interference. The folding algorithm is very good at getting rid of small levels of interference. And if you look very closely, you certainly could see it in the presentations this morning. You can see a faint line down here, and the faint line actually is a bit clearer on the frequency scale. But if you look at the DM chart, the dispersion measure chart, you can see a very fine peak there. The dispersion measure for BO329 is about 26.7, and you can see that that is peaking up at the right place. The period scan and the period rate scans are a bit wobbly, but they do still show a nice peak in that area. And in the colourful plot, the cross is in the red. So from this, you can be pretty sure that that is a pulsar. RF interference, I've mentioned it a couple of times. There's so many sources of RF interference, and I've not got to the bottom of them. You can't identify where they all come from. But it's any modulated signals, digital TV, cell phones, transients, motor car ignition, people's hand tools, mowing machines, solar panels are very great interference, PCs, and large out-of-band saturating signals. What I'm thinking about there is that with my system at 600 megahertz, just above 600 megahertz are as an array of digital TV stations. And if the filter doesn't cut these out and they're still of large amplitude, the amplifiers we use, are these high electron mobility transistor amplifiers. They're usually very wide band. They'll probably cover from a few hundred megs to the low thousands, or maybe the high thousands. So there's gain right across this band. And so it's very important that A, you cut down the noise bandwidth by filtering, but B, you cut out these very large signals. So you need a good band defining filter and RFI mitigation techniques prior to folding. The Presto software has got a lot of easy to use tools. that'll remove RFI in time and in frequency. And they can also block out sections of bad RFI. But you've got to concentrate on identifying a low RFI band when you choose a frequency and you choose a band to operate in. The radio astronomy bands at 400 megs are about from 405 to about 415. But you'll notice that people have used 422. It's because there are some interfering sources in the radio astronomy band, so you can't always bank on that. But at the end of the day, the best results I've ever had have been in nighttime and early morning runs, and you've got to wait for the right time of the year for that.
Peter, I'm sorry, 4-minute warning.
Okay, thank you very much. This is my system, so I'll race through it. It's twin Yagis. As I said, it was the wrong decision. This is I usually get around about 4.5 to 1, 4 to 5 to 1. If you look at the Presto plot, you look at the DM, indeterminate, period, indeterminate. The reason it's indeterminate is that they use this reduced chi-squared, and the point is that with low signal to noise ratios, it doesn't deviate the distribution very far away from Gaussian. So to validate weak signals, I've developed this 8-point check plan. The first test is it the right period and is it the right pulse width? And the blue dots are is a Gaussian pulse of the right one. So that looks right, but some of these noise peaks, they could pass that test. The next test is half file correlation, where you split the file into two. There's a lower half, a blue, the upper half. You fold them separately, overlay one on the other, and a pulsar should always overlap in the center. But as you can see, so do some of these noise spikes. So it's not a strong test. The other thing you can do is fold periods in pairs. So instead of stacking one on top of the other, you stack them on top of the other in pairs, and then you get two pulses in one fold, and you cut that in half, then overlay one on the other, and you see once again this is there, and there are some differences in the others. I use 3 bands, so I can do 3 sub-band correlation. Once again, I get correlation at the right time, and there's far less triple overlap here. So sub-band correlation is a bit of a stronger test. The next one is period search. You do period search in Presto, but all you're looking for there is just an amplitude variation away from the correct period. This is changing the period by 1, 2, and 3 parts per million. But in fact, if you actually do the sums, you can predict exactly what the peak position shift should be. So as well as an amplitude profile, analytically, you can get more information. You can use Presto to do this, get this information, but it's a bit laborious. But you can do it separately yourself. So basically, as you increase the period away from the true period, the pulse broadens and the amplitude goes down. It happens less for noise pulses, but it's very clear. The other one is dispersion search, and you can do that manually. And once again, for dispersion search, you get an amplitude change which you can predict, and you can get a pulse width change that you can predict. Now, the work I've done that has been very interesting is I noticed that when you do half-fold correlations, that sometimes they correlate and sometimes they don't, but the pulsar always does. So I thought, well, let's multiply just the pulsar. If it's there, it's going to be positive. So let's just look at the positive side and multiply the two together. And if you do that, it gets rid of a lot of potential pulsars. It'll get rid of that one, for instance. Now, the other thing you can do is, as it's digital, you can split your half fold into periods. And then what you can do is I could take that period and put it there. And I could take that period, I could take that period and put it there. In fact, I could randomize all these periods. And then if I randomize them and then do a half fold, I'll lose some more peaks because the noise doesn't correlate, but the pulse always does. And if I've done that 50 times and produced this plot down here. So the red is the original fold and the blue is the result of this half-fold correlation with 50 randomizations. And you'll notice the property that it's got is that the pulsar is always the same height, and it's always the right width, and it doesn't change, whereas the noise eventually all removes. To test it, I put in a simulated pulse. So with the live data, I added a simulated pulse at 3.5 to 1 signal-to-noise ratio and did the same process. And you can see that both of those are there. This seems to be quite a strong test. I won't say that it's a 100% positive test. What I will say is it will pick out potential pulsars. I've done this with a number of data records, and it always finds the pulsar, what I think is the pulsar. Okay, so conclusions. Vela and B0329 can be detected in those low frequency bands using homemade small aperture antennas. The main design requirement is for a low antenna side and back load. All the rest of the components are easy to obtain. And understanding pulsar pulse train properties is key to identify low signal-to-noise ratio pulsars in RFI and noise. Thank you very much.
Okay, any questions? I think you answered Wolfgang's in the chat.
Yeah, and with Wolfgang's, you can actually calculate the time that it's in, so that you do need to program the data collection software for the right time.
Okay. I got a John Colt, great talk. Thanks, Peter. Great job, Peter, from Kevin McManus. So you're getting great job.
Okay, thanks very much.
Yeah.